4 days, 2 explosions, 0 warning. A 7-ton rock detonated over Ohio, and the entire planetary defense network missed it completely. Then, before the dust had settled, it happened again, this time over Houston, the 4th largest city in America. 1 ton of space rock travelling at 35,000 miles per hour, breaking apart directly above 7 million people. No alarm, no countdown, no alert on any screen anywhere. And here is the part that nobody is saying loudly enough a piece of it may have come through someone's roof. 2 cities, 4 days, 6 events in 20 days total, and not a single detection system saw any of them coming. Stay with me. Because what's actually happening is stranger than the headlines suggest. If this has you hooked, subscribe to the Skylab, because we are following this story in real time, and when those lab results come back, you will want to be here the moment we crack it open. Leave a comment and tell us honestly, if 2 rocks hit 2 American cities in 4 days with 0 warning, do you feel like the systems designed to protect this planet are doing their job? We genuinely want to know what you think. Now, let us get into it. Part 1. 2 explosions 4 days apart. That's the problem. Something exploded over America and nobody saw it coming. Not once, twice, 4 days apart, over 2 of the most populated regions in the United States. And the systems we built to protect this planet, the telescopes, the satellites, the planetary defense networks, every single one of them was looking somewhere else. Let's start with Ohio, March 17th, 2026. A 7-ton rock travelling at roughly 45,000 miles per hour entered Earth's atmosphere and detonated somewhere over the state, with the energy equivalent of approximately 250 to 370 tons of TNT. To put that in context, that's not a firecracker, that's not a bottle rocket, that's the kind of energy release that, if it had happened slightly lower, slightly slower, slightly differently, would have shattered windows across entire counties. It lit up the sky. It shook the ground. People across multiple states looked up and had no idea what they were seeing. NASA confirmed it through their space alert system after the fact. After the fact. Now hold that in your mind for exactly 4 days. March 21st, 2026. Houston, Texas. 4th largest city in the United States. 7 million people spread across a metro area the size of some small countries. A 1-ton meteor, smaller than the Ohio object, but don't let that comfort you yet, comes screaming in at approximately 35,000 miles per hour and breaks apart somewhere over the northern suburbs. Sonic booms roll across the metro like thunder from a sky with no clouds. Houses shake, car alarms go off. People step outside and look up and see nothing, because by the time the sound reaches them, the object that made it has already ceased to exist in any recognizable form. NASA confirms it. The American Meteor Society logs over 100 eyewitness reports almost immediately. 2 major airbursts, 4 days, 0 warning for either one. Before we go any further, it helps to know what we're actually talking about when we use words like fireball, bolide, and airburst, because these terms get used interchangeably on social media, and they do not mean the same thing. A fireball is simply a very bright meteor, brighter than the planet Venus in the night sky. A bolide is a specific type of fireball that explodes during its descent. It doesn't just streak across the sky, it detonates. An airburst is what happens when a bolide releases most of its energy in the atmosphere before reaching the ground. The most famous modern example is the Chelyabinsk event over Russia in February 2013, a 20-meter rock that nobody detected in advance, that released energy equivalent to roughly 30 times the atomic bomb dropped on Hiroshima, and that injured over 1,500 people from shockwave and shattered glass alone. And Chelyabinsk wasn't even the biggest thing to come through unannounced. What Ohio and Houston gave us were smaller events than Chelyabinsk, significantly smaller. But that framing only provides comfort if you're thinking about physics in isolation. Think about it geographically instead. The Chelyabinsk object detonated over a moderately populated Russian city. Ohio's object passed over a populated state. Houston's object broke apart directly over one of the largest urban concentrations in North America. Same category of event, very different potential outcomes depending on exact trajectory, altitude of maximum energy release, and the direction the shockwave travels. The difference between a news story and a catastrophe is sometimes measured in miles, or in minutes, or in the angle of approach. Here is the part that should make you pause for a moment. Neither event was predicted. There was no potential impact notice from the Center for Near-Earth Object Studies. There was no Planetary Defense Coordination Office alert. There was no countdown clock on a NASA webpage. These objects arrived the way a stranger walks into a room, silently, suddenly, and without an invitation. We found out about them the same way people throughout human history have always found out about things falling from the sky, because it happened and then people reported it. The American Meteor Society's surge in Houston reports, over 100 eyewitness accounts logged in a short window, tells you something important about what people experienced on the ground. These weren't distant flickers visible only to astronomers. People heard it. They felt it. Their walls vibrated. This is what a relatively small space rock does over a major city in the early 21st century. With all of our technology and all of our preparedness, it shows up, it announces itself. And then science scrambles to catch up. Now you might be sitting there thinking, okay, 2 events, bad luck, probably a coincidence, and you might be right. But here's the thing about patterns. They don't announce themselves politely either. They show up in the data quietly, and by the time you've noticed them, several more data points have already arrived. Because Ohio and Houston, they are not the beginning of this story. They are just the 2 that happened over cities. In the 20 days before Houston, there were at least 6 significant fireball events logged globally. 6. And we're going to walk through all of them before this is over. But first we need to go back to Houston, because the Houston event isn't just a story about a rock exploding in the sky over a city. It's a story about what that rock did next, where it went after the explosion, and what one woman in Spring, Texas found inside her house when she walked upstairs to investigate a very loud sound. Houston was the smaller event, and somehow Houston may have been the more dangerous one. Part 2. Houston was smaller, but more dangerous. Size is not the whole story, and Houston is proof of that. When you first see the raw numbers side by side, Ohio looks more impressive. A 7-ton object, speeds approaching 45,000 miles per hour, an energy yield somewhere between 250 and 370 tons of TNT equivalent. Those are genuinely extraordinary figures. By any measure, Ohio's object was the larger, faster, more energetic event. And yet, when scientists and planetary defense researchers start talking about what actually matters in these events, not just the physics of the object itself, but the physics of the object meeting the planet where people actually live, Houston starts to look a lot more concerning. Here is why. Kinetic energy scales with mass and velocity, yes. But risk doesn't scale the same way kinetic energy does. Risk scales with proximity, with population density, with altitude of fragmentation, with the direction and strength of the shockwave that results. A 7-ton rock that detonates at high altitude over rural farmland is a spectacular light show. A 1-ton rock that breaks apart at relatively low altitude directly over 7 million people is a different kind of problem entirely. Houston's object first became visible to observers at approximately 49 miles altitude. That sounds high. It is high. But here's where it gets interesting. The breakup, the moment of maximum fragmentation, occurred at approximately 29 miles above the Bammel area in the northern suburbs of Houston. 29 miles. To put that in perspective, commercial aircraft cruise at roughly 6 to 7 miles altitude. Weather balloons typically reach about 19 miles before they burst. 29 miles is not the edge of space in any meaningful practical sense. It is close, uncomfortably close. It is close enough that the shockwave generated by the fragmentation event had a much shorter distance to travel before reaching the ground than if the object had broken apart higher in the atmosphere. This is not a minor technical detail. Altitude of maximum energy release is one of the most critical factors in determining surface effects. The Chelyabinsk object, which caused over 1,000 injuries, fragmented at roughly 14 miles altitude. Houston's object broke apart at 29 miles, which is higher and therefore less dangerous in direct comparison. But the principle holds in the wrong direction too. If Houston's object had been slightly larger, slightly denser, slightly more structurally coherent, it might have descended further before fragmenting. At 15 miles. At 10, the shockwave footprint from Houston already extended approximately 150 miles. That's not a local event, that's a regional event, during daylight hours, which is exactly when the Houston airburst occurred. Daytime fireballs are rarer than nighttime ones, at least in terms of documented sightings. This sounds backwards. Surely we see more things during the day. The issue is that the sky itself is the competition. At night, a bright fireball stands out dramatically against darkness. During the day, even an extremely bright meteor can be washed out by sunlight and go unnoticed by people not directly looking at the right patch of sky at the right moment. The fact that Houston's event was widely observed in daylight tells you something about how bright and dramatic the fragmentation was. It was hard to miss even when the sun was up. Then there were the eyewitness accounts, and these are worth paying attention to not just for their colour, but for what they confirm about the shockwave behaviour. Residents described hearing what sounded like thunder with no clouds in the sky. Others reported their houses physically shaking. Some described it as an explosion that seemed to come from everywhere at once, rather than from a specific direction, which is exactly what you would expect from an airburst shockwave arriving from above rather than horizontally. People in neighbourhoods miles apart from each other reported similar experiences, which is consistent with a shockwave spreading outward and downward across a wide geographic area. Let's think about this for just a moment using a simple analogy. If you drop a stone into still water, the ripples spread outward from the impact point in all directions equally. An airburst shockwave behaves similarly in 3 dimensions. It spreads outward from the point of maximum energy release in all directions, including downward. The larger the energy release and the lower the altitude, the stronger the surface effects across a wider area. Ohio was, in a very real sense, a warning shot that went wide. Houston was closer to impact in every way that matters to people standing on the ground. But here's what Ohio didn't give us, and Houston did. Radar saw it falling. Not the incoming object. We've already established that nobody detected that. But after the fragmentation, after the object shattered into pieces at 29 miles altitude, something remarkable happened. Those pieces didn't all vaporize. Some of them kept falling, and the Doppler radar systems that blanket the continental United States, the same systems that tell meteorologists where rain is falling and how heavy it is, those systems picked up the falling fragments as they descended through trackable altitudes toward the ground. That single fact changes the nature of this story entirely, and we're going to follow that thread directly into something that should not be possible, but apparently just happened, in a neighbourhood, inside a house, through a roof. Part 3. The Doppler radar moment. Nobody is talking about enough. Weather radar was not designed to track space rocks, and yet here we are. Doppler radar works by emitting pulses of microwave energy and then measuring the return signal from whatever those pulses bounce off. Water droplets in clouds, ice crystals in storm systems, the motion of precipitation toward or away from the radar installation. It is an extraordinarily precise tool for tracking what's happening in the lower atmosphere, and it covers the continental United States in an overlapping network dense enough that there are very few significant gaps. When meteorologists look at radar data, they're essentially looking at a continuous moving picture of everything wet or dense enough to reflect a radar signal, within several hundred miles of each installation. Rocks fall faster than raindrops. Rocks are denser than ice crystals. And when those rocks are arriving from a fragmented bolide travelling at hypersonic speeds, they have trajectories and velocities that look absolutely nothing like precipitation. So when the radar operators and the meteorologists analysing Houston's event looked at their data from March 21st, they saw something that doesn't belong in a weather radar image. They saw a descending field of fragments moving downward at speeds and angles that raindrops simply do not achieve. The radar had detected the falling meteorite fragments from Houston's airburst, specifically over the Willowbrook and Northgate crossing areas of the northern suburbs. Take a moment to let that land, so to speak. This was not a complete vaporization event. The Houston object did not simply cease to exist at 29 miles altitude. It shattered, and the pieces, some of them at least, and potentially many of them, survived long enough in their descent to be trackable by ground-based radar systems. That means they were dense enough, large enough, and numerous enough to produce a detectable radar return as they fell through the lower atmosphere. That means some of them may have reached the surface. In planetary science and meteoritics, the area on the ground where fragments from a fragmented bolide land is called a strewn field. The name is almost gentle for what it actually describes, a region potentially spanning miles, sometimes tens of miles, where chunks of extraterrestrial rock landed at high velocity after falling from an explosion in the upper atmosphere. Strewn fields can contain fragments ranging from microscopic dust particles to rocks the size of your fist or larger. The distribution is not random. It follows the trajectory and the aerodynamics of fragmentation, which means scientists can use radar data, eyewitness reports, and atmospheric modelling to produce predictions about where the densest concentration of fragments should have landed. The historical precedent for this kind of radar-assisted meteorite hunt is well established. In April of 2012, a bolide detonated over northern California, and radar data was used to locate the resulting strewn field near Sutter's Mill, the same site where gold was first discovered in 1848, which is either a remarkable coincidence or just California being California. The Sutter's Mill meteorite recovered from that event turned out to be a carbonaceous chondrite, one of the most scientifically valuable types of meteorite because of its primitive composition dating back to the early solar system. Radar made recovery possible. Houston's radar data now creates the same possibility, with one additional complication that Sutter's Mill didn't have. Sutter's Mill is a historical park surrounded by relatively open terrain. The Willowbrook and Northgate crossing areas of Houston are dense residential suburbs. Houses, cars, roads, yards, shopping centres, schools. If the fragments indicated by radar actually reached the ground, and the physics strongly suggests some of them did, they didn't land in an empty field waiting to be collected by scientists in protective gloves. They landed in a neighbourhood, on rooftops, in backyards, possibly through windows, possibly through something harder to repair than a window. Think about what a strewn field over a suburban neighbourhood actually means in human terms, not just scientific ones. Imagine it raining rocks. Not heavily, the fragments would be spread across miles but steadily, silently, invisibly, in the seconds and minutes following the airburst. Most people on the ground would have been reacting to the sonic boom, looking at the sky, calling their neighbours. They wouldn't have known that some percentage of what had just exploded above them was now descending toward their homes at terminal velocity. Radar-confirmed meteorite falls over populated areas are genuinely uncommon. Most falls happen in remote regions, in the ocean, in unpopulated terrain. The combination of a populated target zone, radar confirmation of descending fragments, and the spatial specificity of the Willowbrook and Northgate area creates what scientists call a high-confidence recovery scenario, meaning if you go look in the right places, you are likely to find something. And it turns out someone may not have had to go anywhere to find it. It may have come to her. Part 4. The roof impact case. If confirmed, this changes the month. A woman in Spring, Texas heard a loud boom, and then she heard something else, something closer, something inside her house. Spring is a community in the northern suburbs of Houston, sitting directly within the area identified by Doppler radar as the most probable landing zone for fragments from the March 21st airburst. The timing was right, the location was right, and when this resident investigated the sound she heard following the initial sonic boom, she found a hole in her ceiling and a rock on her floor that had not been there before. The object was reportedly football-sized, dark on the exterior, and unusually heavy for its apparent dimensions. When the fire department responded and examined the object, their assessment was that it was an unusual rock with no alternative explanation readily available on scene. Now, critical point, and this matters enormously, the fragment has not been officially confirmed as a meteorite by scientific laboratory analysis as of this reporting. Confirmation requires chemical and isotopic testing by qualified researchers. You cannot look at a rock and declare it a meteorite, even if it fell through your roof during a meteor event. Rocks can enter attics from other causes. Debris travels in unexpected ways. Science requires verification before making claims of this magnitude. So we hold this case in the category of extremely compelling and pending confirmation, not established fact. That said, let's talk about what confirmation would mean. Documented cases of meteorites striking occupied dwellings are extraordinarily rare in the historical record. The most frequently cited case is the Hodges meteorite of November 30th, 1954, when an 8.5-pound stone crashed through the roof of a home in Sylacauga, Alabama, bounced off a radio console, and struck Ann Hodges on her hip while she was sleeping on a couch. She survived. The meteorite is now in a museum. That event stands as the only confirmed case of a human being directly struck by a meteorite in recorded history. Houses have been hit by meteorites, but rarely, and the documentation of such events is sparse precisely because they are so uncommon. Now consider what happened in Germany just 13 days before Houston, on March 8, 2026. A meteorite struck a rooftop in Koblenz-Gulz, a district of the city of Koblenz in western Germany. That event was confirmed. It was documented. A rock from space hit a building in a European city, and scientists recovered it, and the world largely moved on because any single such event can be filed under rare, but not unprecedented. Here is where the mathematics starts feeling uncomfortable. If the Spring, Texas case is confirmed, we would have 2 documented residential or rooftop impacts by space rocks within approximately 13 days of each other on 2 different continents. The statistical baseline for such events globally is measured in events per decade, not events per fortnight. Independently, each event is unusual but explainable. Together, they require a more careful look. Together, they begin to suggest that either we are in a period of elevated activity, or that our detection of such events has suddenly become dramatically more efficient, or both. There is a speculative dimension here that some researchers are already quietly discussing, which is this. If the Spring, Texas fragment and the Koblenz-Gulls fragment are both recovered and analysed, and if their chemical signatures share unusual features, particularly in their oxygen isotope ratios or trace element compositions, that would represent a scientific data point of significant interest. Not proof of anything, not yet, but a data point. Chemistry doesn't lie about where a rock came from. 2 rocks from the same source would carry matching fingerprints, regardless of where they landed. But we're getting ahead of the data, which is what good journalism should resist and what the human brain desperately wants to do. What we can say with confidence is this. In a single week, the abstract question of space rocks entering the atmosphere became, for at least one person in suburban Houston, a very concrete and personal experience. This is not a news story about something that happened up in the sky. For her, it happened in her living room. Space came to visit, and it didn't knock first. And here's what makes the following question unavoidable. How many other impacts in that strewn field went unnoticed, unreported, or unrecognised, because they landed in a backyard, not a bedroom? Part 5. The cluster problem just got worse. 2 events over American cities in 4 days would be enough to raise eyebrows on their own. But the timeline doesn't start on March 17th. It doesn't even start in the week before that. If you pull back and look at the full picture of significant fireball events in the approximately 20 days leading up to Houston, you find something that stops being easy to dismiss as coincidence and starts requiring a more considered explanation. March 2nd, 2026. A significant fireball over Louisiana, documented by multiple witnesses and confirmed by detection networks. March 3rd, 2026. Another event over the Pacific Northwest, visually observed across a multi-state region with multiple eyewitness reports logged with the American Meteor Society. March 8th, 2026. The Koblenz-Gulls rooftop impact in Germany, a confirmed meteorite landing on a residential building in a European city. March 17th, 2026. The Ohio airburst, 7 tons, equivalent to several hundred tons of TNT, zero advanced detection. March 20th, 2026. A significant detection event in the South Pacific picked up by infrasound monitoring networks. March 21st, 2026, Houston. That is 6 significant events in approximately 20 days. 6 events featuring sonic booms, fragment survival, multi-state or multi-country visibility, or instrument confirmation, in a 20-day window, over a geographic spread that includes North America, Europe, and the South Pacific. To understand why that matters, you need a brief baseline comparison. Earth is hit by space rocks constantly. The planet sweeps up an estimated 40 to 80 metric tons of extraterrestrial material every single day, most of it in the form of microscopic dust. Actual fireball events visible to the naked eye happen globally at a rate of roughly several per day, most over unpopulated areas, most too small to produce sonic booms or surviving fragments. Major events, bolides of the scale we're discussing, are less common. Events producing sonic booms and confirmed fragment survival are rarer still. 6 such events in 20 days is not the baseline. It is above the baseline by a margin that deserves attention. Here is the detail that makes this cluster most unusual, and it's a detail we'll explore more deeply in the next part of this story. None of these events have been linked to any known active meteor shower. When Earth passes through the debris trail of a comet, or through a known concentration of material in its orbital path, we expect meteor showers. We see them on schedule. The Perseids in August, the Leonids in November, the Geminids in December. These showers have known radiance, specific points in the sky from which all the meteors in a given shower appear to originate, because they are all travelling in the same direction from the same source. The events of late February and March 2026 share no common radiant. They are coming from different directions. They have different velocities. Their trajectories, as reconstructed from witness reports and instrument data, don't point back to a single origin. In meteor science, objects without a shower affiliation are called sporadic meteoroids, essentially random debris floating in the inner solar system that happens to intersect Earth's path by coincidence of orbital mechanics. Sporadic events happen all the time. What doesn't happen all the time is a concentrated cluster of significant sporadic events within a 20-day window with no apparent shared origin. When things that should be random start clustering in time and space without an obvious common cause, science has a word for that condition. It calls it a pattern, and patterns demand explanations. The innocent explanation is that we are simply in an elevated period of random activity, a statistical fluctuation within normal ranges that feels unusual because we're tracking it more carefully than we used to. The less innocent explanation is that something has changed in the near-Earth environment, something we haven't fully identified yet, and we are seeing its effects arrive one event at a time, over cities and oceans and rooftops, with no warning and no catalogue entry and no name. The systems we built to tell us when something is coming didn't see Ohio. They didn't see Houston. So the real question isn't just why so many events are happening. The real question is, what else is out there right now that we can't see? Part 6. The detection gap is no longer theoretical. For years, planetary defense experts described a detection gap as a theoretical vulnerability, a known weakness in our surveillance systems that could, in principle, allow a dangerous object to arrive undetected. Ohio and Houston just made it empirical. The infrastructure humanity has built to find threatening objects in space is genuinely impressive at what it's designed to do. Ground-based telescope networks like the Catalina Sky Survey and Pan-STARRS scan large areas of sky repeatedly, building catalogues of near-Earth objects and flagging anything that appears to be on a collision course with Earth. Space-based infrared surveys detect objects that reflect poorly in visible light but emit heat. The Center for Near-Earth Object Studies maintains a constantly updated catalogue of known objects and their orbital parameters. NASA's Planetary Defense Coordination Office serves as the central hub for threat assessment. These systems, collectively, have found hundreds of thousands of asteroids and catalogued nearly all of the large ones, objects over a kilometre in diameter that could cause civilization-level damage on impact. But here is the threshold problem, and it is not a secret. The detection systems we have are optimised for large objects. Objects over a kilometre in diameter are almost all catalogued. Objects over 140 metres in diameter, the rough threshold above which regional devastation becomes possible, are estimated to be catalogued at roughly 40% completion. Objects below 50 metres in diameter, the size range that includes both Ohio's 7-ton impactor and Houston's 1-ton object, are essentially invisible to current systematic detection efforts. There are simply too many of them. They are too small to reflect enough light for current telescope sensitivities to reliably detect at meaningful distances, and many of them are in orbital configurations that make advanced detection extremely difficult. The blind spots have geometry as well as scale. Objects approaching from the direction of the Sun are fundamentally difficult to detect from Earth's surface. Solar glare drowns out the reflected light from incoming rocks in that part of the sky. This is why some researchers have advocated for space-based detection assets positioned away from Earth, at different orbital vantage points, to watch the Sun-facing approach vector that ground telescopes can't easily cover. The DART mission demonstrated that we can deflect an asteroid if we know it's coming, and have enough lead time. The Ohio and Houston events demonstrate that we may not always have either. The frequency problem compounds the scale problem. Small objects, let's define these loosely as objects under 10 meters in diameter, are estimated to impact Earth's atmosphere somewhere between several times per year for the larger end of that range, to multiple times per day for objects the size of a large car. The vast majority of these events happen over the ocean, in uninhabited regions, or produce fireballs too small and too high altitude to be noticed at ground level. But the distribution is random, and random means that occasionally multiple events cluster together by chance, and occasionally the random landing point is a populated area rather than open water. We are reactive, not predictive, in the size range that produced Ohio and Houston. Full stop. There is no system currently operational that would have detected either object with meaningful advance warning, not hours, not even minutes. The detection gap for meter to 10 meter objects is not a funding shortfall that's about to be fixed. It is a fundamental limitation of current technology deployed at current coverage levels. We find out about these events the same way the public does, after they happen, from the light they produce and the sound they make on the way down. What makes this moment particularly interesting, in a way that is equal parts reassuring and unsettling, is that the detection gap is not permanent. The tools to close it, or at least substantially narrow it, either exist in prototype or are in active development. The question is whether we're moving fast enough. Because the objects are not waiting for us to build better telescopes. They're arriving on their own schedule, and that schedule, as the last 20 days have shown, does not accommodate our timelines. But here's a wrinkle that makes the detection gap even stranger in this specific case. Ohio and Houston didn't just come from the wrong direction, or the wrong size class for our systems to catch. They may have come from the wrong direction in a deeper sense, a directionality problem that goes beyond solar approach angles and gets into something much more puzzling about where these objects are actually coming from. Part 7. The direction problem. No radiant, no pattern. Every meteor shower in the calendar has a radiant, and a radiant is one of the most useful things in astronomy. Not because it is visually spectacular, though it can be. Not because it tells you where to point a camera for the best photographs, though it does that too. A radiant is useful because it is information. It is the sky telling you, in the most direct geometric language available, where a collection of objects came from, and in a story where the central mystery is the origin of an unusual cluster of space rocks arriving over populated areas without warning. The question of whether those rocks have a radiant, a direction, a source, a traceable origin, is not a technical footnote. It is the question that everything else depends on. Here is how a radiant works, stated simply enough to carry the concept forward without losing anyone. When Earth moves through a stream of debris in space, the remnant trail of material shed by a comet over many orbits, spread along the comet's path like crumbs left by a very large and very slow traveller. The individual particles in that stream are all moving in roughly parallel paths relative to Earth. They are a fleet travelling in formation. When you watch them enter the atmosphere from the ground, the geometry of perspective makes them appear to diverge from a single point in the sky. The same optical illusion that makes parallel railroad tracks appear to converge at the horizon when you look down them from one end. That convergence point in reverse, the point in the sky from which the meteors appear to radiate outward, is the radiant. It marks the direction from which the stream is arriving, and because streams are associated with specific comets on specific orbits, the radiant tells you not just a direction, but an origin story. The Perseid meteor shower, which peaks every August and is probably the most widely observed annual shower from the northern hemisphere, has its radiant in the constellation Perseus. Every Perseid meteor appears to streak away from that region of sky, because every Perseid particle is a fragment of Comet 109 P Swift-Tuttle, arriving at Earth along a trajectory that geometry projects back to Perseus from the observer's perspective. The Leonids in November radiate from Leo. They are debris from Comet 55 P Tempel-Tuttle. The Geminids in December radiate from Gemini. Unusually, they come not from a comet but from an asteroid designated 3200 Phaethon, which appears to be a dormant or extinct comet that has shed a debris trail nonetheless. In every case, the radiant is fixed and predictable from year to year, because the debris stream producing it is stable, its orbit characterized, its geometry understood. You can predict where the radiant will be decades in advance, because you know where the parent body's trail lies relative to Earth's orbit. Sporadic meteors, the ones with no shower affiliation, no parent body, no debris stream, don't have a consistent radiant because they are not part of any stream. Each sporadic is an individual object on its own unique orbital path, a piece of the solar system's general debris population that happens to intersect Earth's orbit at this particular moment, rather than being part of an organized flow. Their directions are effectively randomized across the sky. They come from everywhere and from nowhere specific. This is normal. This is expected. The majority of fireballs observed on any given night that don't coincide with a known shower are sporadic, and their random directionality is not a puzzle. It is the definition of the category. But here is where the late February and March 2026 cluster stops fitting neatly into any available category, and where the researchers who have been examining the trajectory data most carefully have been, in the careful, hedged, professionally cautious language of scientists who are not yet ready to make a claim they cannot fully defend, quietly flagging something that doesn't resolve easily. The directional data for the March cluster is not just non-shower, it is actively contradictory in ways that are difficult to explain even under normal sporadic assumptions. The trajectory reconstructions produced from witness reports, Doppler wine profiler data, infrasound arrival angles, and all sky camera observations don't point back to a consistent region of the solar system across the events. More specifically, some of the directional estimates produced independently by NASA's Meteor Environment Group and by the American Meteor Society for the same individual events have shown notable discrepancies, differences in reconstructed approach direction that are larger than typical measurement uncertainty would account for. This could mean that the trajectory reconstructions themselves carry significant uncertainty, which is entirely possible when the data quality varies across events and observation networks. But it could also mean something more interesting, that the approach vectors are genuinely complex, that multiple events are arriving from directions that don't cluster the way a common origin population should. Here is why that matters in a way that goes beyond the technical details of meteor trajectory reconstruction. If you have a collection of sporadic meteors that all originated in the asteroid belt, the broad region between Mars and Jupiter, where the majority of small solar system debris resides, where the cumulative gravitational influence of Jupiter over billions of years has prevented the formation of a planet and instead maintained a population of rocky objects ranging from microscopic dust to bodies hundreds of kilometers across, you would expect their orbital parameters to show a statistical family resemblance even in the absence of a specific shared origin. Asteroid belt objects arrive at Earth with particular velocity ranges determined by their orbital energies. They have particular inclination distributions reflecting the flattened structure of the main belt. Their approach geometries when they intersect Earth's orbit cluster in ways that reflect the dynamics of how material escapes the belt and reaches Earth-crossing orbits. They should look similar in a statistical sense, even if each individual object is on its own unique path. They should not look like they are arriving from multiple directions that don't share the family resemblance of a common source region. Think about it this way. Imagine you're standing in a room and you're trying to determine where dust in the air is coming from. If the dust is simply settling from general suspension in the air, what happens in any room after disturbance, as particles slowly fall from every direction under gravity? The distribution of particle arrival directions will be approximately uniform across the hemisphere above you. That is what normal sporadic meteor directionality looks like from Earth's perspective. Random, uniform, coming from everywhere equally. Now imagine that instead of general suspension, someone has set up a fan somewhere in the room and is blowing concentrated dust toward you from a specific direction. The distribution is no longer uniform. It has structure. It has directionality. Even if the fan is pointed at a diffuse angle rather than directly at you, even if the room's air currents spread the dust somewhat, the distribution will be non-uniform in ways that betray the existence of a source. The March cluster looks, in some analyses, less like settling dust and more like a room with a fan somewhere that nobody has located yet. Not a focused beam, there is no clear radiant, no single point of origin that jumps out of the data the way a shower radiant does, but something more directionally structured than pure random sporadic background, something that resists the easy categorization of ordinary asteroid belt debris arriving in ordinary proportions from ordinary directions, something diffuse and non-uniform and not yet named. This raises a possibility that some researchers have been willing to state carefully in informal scientific discussions, while others have maintained professional caution about committing to in print, and it is a possibility that becomes more interesting the longer you look at the trajectory data without finding a clean explanation. Earth may currently be moving through a region of space that contains an elevated local density of small debris without a catalogue entry. Not a known comet trail with a named parent body, not a known asteroid family with characterized membership, something scattered, something diffuse, something that exists at a density too low to have been detectable by any survey system operating before now, but high enough that when Earth moves through it, the intersection rate for city-scale objects rises above the background level in a way that produces a March 2026 rather than a typical quiet month. We have always operated under the assumption that the space environment Earth moves through is well characterized at the size scales that matter for human safety. The large objects are mostly catalogued, the shower streams are mapped, the general sporadic background is understood statistically if not individually. But what if there are concentrations of material in the inner solar system, diffuse, extended, not associated with any known parent body, invisible to any instrument we have yet deployed, that we simply have no tools to detect until they start producing events? What if the map of the near-Earth debris environment has blank regions that we labelled as empty, not because we looked and found nothing, but because we never had instruments sensitive enough to look properly? That question has an answer that the planetary science community has been developing for months, an answer that gained substantial new momentum after Houston, and it involves a visitor from outside the solar system, a debris trail left behind during a gravitational encounter with our Sun, and a timing that is either a remarkable coincidence or the first data point in a pattern that the isotope laboratories are currently racing to either confirm or rule out. The direction problem doesn't have a clean solution yet, but the most compelling candidate explanation is already on the table, and it came from very, very far away. Part 8. The 3I Atlas Debris Hypothesis Revisited Under Pressure. In late 2025, an interstellar object designated 3I Atlas passed through the inner solar system, and most of the world did not notice. This is not surprising. The detection of interstellar objects passing through our solar system is a relatively new capability, one that depends on survey telescopes sensitive enough to find fast-moving objects with unusual trajectories against the background of normal solar system debris, and software sophisticated enough to flag the orbital solutions that indicate hyperbolic paths inconsistent with any origin within our own Sun's gravitational family. Before Oumuamua in 2017, we had never confirmed the detection of an object from another star system passing through our solar neighbourhood. The instruments to find them reliably simply didn't exist at operational scale. Now they do, and the result is that we are beginning to discover how frequently the galaxy sends visitors through our cosmic backyard, and how little we understood, until recently, about what those visitors might leave behind. Oumuamua arrived in 2017, and immediately became one of the most debated objects in the history of astronomy. Its elongated shape, unusual acceleration that couldn't be fully explained by gravity alone, and complete absence of the cometary outgassing that normally drives non-gravitational acceleration in small bodies, produced a scientific literature of remarkable volume and remarkable disagreement in a very short time. Whatever Oumuamua was, and the debate about its nature has not fully resolved, it passed through and departed without leaving any physically recoverable material behind, at least none that we detected. Borisov arrived in 2019 and was in many ways more straightforward. It displayed cometary activity, shed gas and dust as it approached the Sun, and behaved in ways that fit cometary models developed for solar system objects reasonably well despite its interstellar origin. Borisov also departed without leaving a detectable debris field in Earth-crossing orbits. 3I Atlas was different in ways that matter enormously to the hypothesis currently under examination, the trajectory. 3I Atlas followed during its late 2025 perihelion passage. Its closest approach to the Sun was more deeply penetrating into the inner solar system than either of its confirmed interstellar predecessors. Deeper perihelion passages mean stronger solar radiation pressure, stronger tidal gravitational forces, and greater thermal stress on the object's structure during the period of maximum solar proximity. For an object that is loosely consolidated, what planetary scientists call a rubble pile, a gravitationally bound aggregate of smaller pieces rather than a coherent solid body, these forces can exceed the structural strength holding the aggregate together. The result is not necessarily a dramatic visible fragmentation event of the kind that produces a spectacular display. It can be a quiet, gradual shedding of material, smaller fragments spinning off the surface, dust and gravel and fist-sized rocks released into orbits that are similar to the parent object's path but not identical, spread by the geometry of release and the subtle differences in solar radiation pressure acting on objects of different sizes and compositions. Interstellar objects are travellers. They arrive from other star systems on hyperbolic trajectories, paths that are not closed, ellipses bound to our Sun but open curves that carry them in from interstellar space, curve around the Sun at perihelion, and then carry them back out on a departure trajectory aimed at a different region of the galaxy than the one they came from. The Sun's gravity captures them temporarily in the sense that it deflects their path, but it does not hold them. They visit and they leave, typically within months of their closest approach. 3I Atlas is, as of this writing, long gone from any region of space where direct observation would be practical. It has been flung back into the interstellar medium on its post-perihelion trajectory, receding at the hyperbolic excess velocity that characterized its approach, heading toward a destination in the galaxy that will take it millions of years to reach. But here is the thing about travelers who pass through a place and leave things behind. The traveler departs. The things left behind stay. The 3I Atlas debris hypothesis, as it has come to be called in the informal scientific discussions that precede formal publication, when researchers are still working out whether an idea survives contact with the data, proposes a mechanism that is physically plausible and temporally specific. If 3I Atlas shed material during its late 2025 perihelion passage, and the characteristics of its trajectory and the dynamical modelling of what happens to loosely consolidated objects during deep inner solar system passages suggest this is a genuine possibility rather than a speculative fantasy, then some of that material would have been released into orbits that remain within the inner solar system after the parent object's departure. The precise distribution of those orbits depends on the geometry of the release, the sizes and compositions of the released fragments, and the subsequent gravitational and radiation pressure evolution of the debris cloud. But the general result of such a release would be a diffuse cloud of material spread along and around the parent object's former orbit, thickest near the point of release and thinning with distance, evolving slowly over time as individual fragments respond to the gravitational influences of the inner solar system planets. The timing calculation is the part of this hypothesis that gives it its most compelling feature. Earth's orbit intersects the region of the inner solar system where 3I Atlas reached perihelion. The geometry of orbital mechanics places Earth moving through the region of densest expected debris concentration from a late 2025 perihelion shed event in the window of late February through April of 2026. Not vaguely in that general era, specifically in that window, based on the orbital dynamics of how debris spreads from a perihelion release point and how Earth's own orbit carries it through that region. The temporal correlation between the predicted debris encounter window and the observed cluster of March 2026 events is, at minimum, striking enough to demand serious attention rather than dismissal. The non-directional nature of the impacts, the absence of a radiant, the directional incoherence that makes the cluster so difficult to categorize as normal sporadic background, fits naturally into this framework. Debris shed from an interstellar object during perihelion passage would not form a tight, coherent stream like the debris trail of a periodic comet that has made hundreds of passes through the inner solar system and had its material organized by repeated gravitational interactions into a well-defined structure. It would be diffuse, scattered, spread across a broad range of orbital inclinations and eccentricities, reflecting the chaotic geometry of release from a fast-moving, deeply penetrating object on a hyperbolic trajectory. It would look, from Earth's surface, like meteors coming from multiple directions with no coherent source region, exactly what the March 2026 trajectory data shows. The hypothesis explains the timing, it explains the directionality. It explains why the cluster doesn't correspond to any known shower period and can't be attributed to any known debris stream. It provides a specific physically motivated mechanism for why March 2026 is different from March 2024 in a way that has nothing to do with statistical fluctuation in the normal sporadic background. These are the features that make it scientifically interesting, and they are genuinely interesting features. A hypothesis that explains multiple independent observations through a single coherent mechanism is exactly what science is designed to reward when the evidence supports it. But here is where intellectual honesty requires the same care that the researchers discussing this hypothesis are applying in their own evaluations. The 3I Atlas debris hypothesis is scientifically premature in a specific and important sense. There is currently no direct physical evidence linking any recovered fragment from the March 2026 cluster to 3I Atlas debris specifically. The orbital dynamics argument is suggestive. The temporal correlation is striking. The directional incoherence fits the model. But none of these observations constitute proof, or anything close to proof, that the objects arriving over Ohio and Houston and the Pacific Northwest and Louisiana and Germany were shed by an interstellar visitor during its perihelion passage. They constitute a case for the hypothesis worth taking seriously. They do not constitute confirmation. The confirmation, if it comes, will come from chemistry. Specifically from the isotope ratios locked into the mineral structure of recovered fragments, the chemical handwriting that distinguishes material formed in our solar system from material formed around another star. Two samples are currently the most promising candidates for this test. The Koblenz-Gülls meteorite from the March 8th German rooftop impact is reportedly in laboratory analysis. The spring Texas fragment, if confirmed as a meteorite, would be a second sample from the same 20-day cluster on a different continent. If both samples show isotopic signatures that fall outside the established envelope of solar system meteorite chemistry, if the oxygen isotope ratios, the chromium ratios, the titanium ratios, any of the standard isotope systems used in meteoritics, come back anomalous in ways consistent with formation in a different stellar environment, that would be confirmation of a kind that orbital dynamics arguments cannot provide. The data will either confirm this or it will not. Science is patient in ways that the human appetite for resolution is not, and the analysis required to make this determination cannot be accelerated without compromising the integrity of the results. Weeks at minimum, months realistically. And in the meantime, the events of March 2026 are not waiting politely for the laboratory results before deciding whether to continue. The debris field, if it exists, is still there. Earth is still moving through whatever region of space produced the cluster. More objects may arrive before the first ones have been fully characterized. More rooftops may be punctured. More strewn fields may be deposited over more neighborhoods. And each new event will add a data point to a hypothesis that is currently sitting in the most uncomfortable and most scientifically productive position available, compelling enough to take seriously, unconfirmed enough to require patience, and consequential enough that the answer, when it comes, will matter far beyond the community of researchers currently waiting for it. Somewhere in a laboratory right now, a rock that fell through a German roof is being asked where it came from. The universe, characteristically, is taking its time answering. Part 9. The isotope test that could change everything. Chemistry is the universe's handwriting, and every rock carries a signature of where it was born. Think about what that actually means for a moment. Every meteorite that has ever fallen to Earth, every fragment recovered from a desert floor, every chunk pulled from Antarctic ice, every rock that punched through a roof or cratered a field or skipped off an atmosphere and burned, all of them arrived carrying a chemical autobiography, a record written not in language but in atomic structure, in the precise ratios of isotopes locked into the mineral matrix at the moment of formation, billions of years ago, in an environment that no longer exists in any form we can visit or observe. The rock remembers where it came from even when we don't know where to look. And right now, in a laboratory somewhere in Europe, a rock from a rooftop in Koblenz is being asked to tell its story. The answer it gives could be the most important thing a piece of stone has ever said. When a meteorite forms, when the dust and gas of a solar nebula condense and accrete into solid material, it locks in a chemical record of the environment it formed in. The proportions of different isotopes of elements like oxygen, chromium and titanium in a given meteorite are diagnostic of its formation region. Solar system meteorites, despite their enormous variety in composition and structure and age, all fall within a characteristic envelope of these ratios. They all formed in the same general chemical neighborhood, around the same star, from similar starting materials distributed through the same protoplanetary disk. That envelope is extraordinarily well characterized by now. Decades of sample analysis from hundreds of recovered meteorites have defined its boundaries with high precision. Scientists know what solar system rocks look like chemically. They know it the way a forensic examiner knows a familiar handwriting sample, intimately, confidently, and with enough experience to recognize immediately when something doesn't fit. Isotopes, if you need the quick version, are variants of the same element with different numbers of neutrons in their nucleus. They behave nearly identically in chemical reactions, but they have slightly different masses, and that mass difference means they partition differently during physical and chemical processes: evaporation, condensation, crystallization, melting. Oxygen, for example, comes in 3 stable isotope forms: oxygen-16, oxygen-17, and oxygen-18. The relative proportions of these 3 isotopes in a rock record the temperature, the pressure, and the chemical composition of the environment where the rock formed. Different regions of the solar system have slightly different oxygen isotope ratios. The inner asteroid belt has a characteristic signature. The outer belt has a different one. Cometary material has its own range. Different types of asteroids have ratios that allow scientists to identify which family a meteorite came from with remarkable specificity. Not just that it's an asteroid, but which neighborhood of the asteroid belt, which formation epoch, which parent body. The chemistry is that precise. and objects formed around other stars in other solar systems with different starting compositions built from material processed in a different stellar environment around a different sun with a different elemental abundance pattern, those objects would carry oxygen isotope ratios that fall outside the solar system envelope entirely, not slightly outside, not ambiguously at the edge, outside in a way that would be immediately recognizable to any isotope geochemist looking at the data. There is no measurement uncertainty large enough to explain away an extrasolar signature if one is present. You would know. The Germany sample from the Koblenz-Gulls rooftop impact on March 8th is reportedly in analysis right now. The researchers working on it have not publicly released results as of this reporting, which is completely normal. Isotope analysis is methodical, painstaking work that cannot be rushed without compromising the integrity of the data. Contamination protocols must be followed. Multiple independent measurements must be made and cross-checked. The chain of custody from recovery to analysis must be documented and defensible. This is not a process that accommodates urgency, regardless of how urgently the rest of the world wants answers. But the questions those researchers are asking that sample include the most fundamental ones available to planetary science. Does this match known solar system meteorite chemistry, or does it show anomalies? Which asteroid family, if any, does it belong to? Are there any signatures, in oxygen, in chromium, in titanium, in the trace element abundances, suggesting an origin outside the inner solar system, outside our solar system entirely? Those questions are being asked of a rock that fell through a roof in Germany on March 8, 2026, 13 days before Houston. 13 days before a 1-ton object detonated over 7 million people, and radar tracked its fragments falling over residential neighborhoods, and a woman in Spring, Texas found something on her floor that should not exist in any house that hasn't been visited by the sky. Now extend that question to Houston. If the Spring, Texas fragment is confirmed as a meteorite, and the circumstantial case for confirmation is compelling, though science requires more than compelling circumstances, and if it is submitted for the same isotope analysis currently being applied to the Koblenz sample, it becomes a second data point from the same 20-day cluster. 2 rocks, 2 continents, 1 extraordinary window of time, and if both samples show anomalous chemistry, not matching known solar system types, showing isotope ratios outside the established solar system envelope, the probability that both results are measurement errors or contamination artifacts drops to something approaching 0. Contamination happens to 1 sample in 1 lab. It does not independently produce the same anomalous signature in 2 separate samples, analysed in 2 separate facilities on 2 separate continents. 2 independent samples, 2 independent analyses, 2 matching anomalies. That is not noise. That is not instrument error. That is not a calibration problem. That is signal, and signal of the most extraordinary kind that planetary science has ever been in a position to detect. What would it actually mean if interstellar material were confirmed in recovered fragments from this cluster? Walk through it carefully, because the implications expand in every direction you look. At the most immediate level, it would validate the 3-eye Atlas debris hypothesis with direct physical evidence, the first time in history that a proposed mechanism for interstellar debris delivery to Earth's surface had been confirmed by laboratory chemistry, rather than inferred from orbital dynamics. It would establish that an interstellar object shed recoverable material during its inner solar system passage in late 2025, something that has never been directly confirmed for any of the interstellar objects previously detected. Oumuamua passed through in 2017, Borisov in 2019. Neither left us anything to hold. 3-eye Atlas, if this hypothesis is correct, left us fragments in a German neighbourhood and potentially in a Houston suburb. That would be without precedent in the history of astronomy. At a larger level, confirmation would mean that the March 2026 events are not merely an unusual cluster of near-Earth space weather to be filed under interesting and forgotten when the next news cycle arrives. They would be the delivery mechanism for an extraordinary scientific gift, samples of extrasolar material, material formed around another star in another planetary system potentially billions of light years and billions of years removed from anything in our own cosmic neighbourhood, that travelled across interstellar space, shed from a passing visitor during a brief gravitational encounter with our Sun, and ended up against all calculable probability in a suburb of Houston and on a rooftop in Koblenz. The universe, in its entirely impersonal and magnificently indifferent way, through as something that scientists have wanted for decades. Physical samples of another star system, not observed through a telescope, not inferred from spectral data, held in a gloved hand in a clean room, weighed on a precision scale sliced with a diamond saw, and interrogated with instruments sensitive enough to read the chemical diary of a rock that was born somewhere we will never go. The question is whether we recognized what it was before it ended up in a contractor's dumpster, before someone swept it off their roof into a garbage bag, before the strewn field over Houston was paved over, built over, landscaped over, and lost to the ordinary entropy of suburban life. Every day that passes between the fall and the recovery is a day in which something irreplaceable may become irretrievable. Analysis takes time regardless. Weeks at minimum, months realistically for complete characterization that would satisfy the peer review process. And here is the part that creates genuine tension that no amount of scientific patience can fully resolve. The events of March 2026 may not be finished yet. More objects may arrive before those results are published. More fragments may fall. More rooftops may be punctured. More strewn fields may be deposited over neighborhoods where people are not yet looking for them. And we will not know whether they are carrying the chemical signature of our own solar system or the handwriting of somewhere impossibly far away until long after they land, long after the analysis is complete, long after the moment of arrival has passed into memory. The rock remembers. We just have to find it before we throw it away. Part 10. Debunking the weapons in the sky theory, without killing the mystery. Every time something explodes in the sky over a major American city, a certain segment of the internet reaches the same conclusion with impressive speed. Within hours of the Ohio airburst, the theories were already circulating. Within hours of Houston, they were trending. And look, this is not criticism exactly, because the impulse behind it is deeply human and worth understanding rather than dismissing. When we encounter something frightening that we cannot immediately explain, the brain does not comfortably settle into uncertainty. It searches, it pattern matches, it reaches for the nearest available framework that converts chaos into agency, randomness into intention, the terrifying impersonal universe into something with a face and a motive and a decision-making process that could theoretically be identified, confronted, or stopped. Natural phenomena that arrive without warning and detonate over major cities feel too random, too impersonal, too completely outside any human capacity to influence or respond to. A weapon, at least, implies someone is in charge. Even if that someone is hostile, even if their intentions are destructive, the existence of an agent means the existence of a negotiation, of a deterrent, of a response. Chaos is more frightening than malice in a strange way, because malice can theoretically be engaged with. Physics cannot be reasoned with. Physics does not care about your rebuttal. So let's engage with the weapons hypothesis fairly, completely, and then put it to rest as cleanly as the evidence allows. The argument as it is typically constructed goes something like this. There have been too many of these events in too short a time period, over too many American locations to be coincidence. The timing correlates with elevated geopolitical tensions globally. Some of the events occurred during periods of heightened military activity in multiple theatres. The objects arrived without warning over some of the most densely populated and strategically significant urban areas in the country. Therefore, the argument concludes, some percentage of these explosions could represent tests of new weapons technologies, hypersonic delivery systems, directed energy platforms, kinetic orbital weapons, or other advanced capabilities that a sophisticated adversary might be probing the American homeland with under the cover of plausible deniability. It sounds, on the surface, like a coherent hypothesis. It even sounds, if you squint at the timeline in the right way, like it fits the data. Here is where the physics becomes unambiguous, and unambiguous is a strong word that the evidence in this case fully supports. Natural meteors entering the atmosphere at velocities of 15 to 20 kilometers per second, which translates to roughly 45,000 miles per hour for the Ohio object and approximately 35,000 miles per hour for Houston, generate very specific optical and spectral signatures that are not replicable by any known artificial system. As a meteor travels through the upper atmosphere at hypersonic velocity, it compresses and heats the air ahead of it to temperatures of thousands of degrees, creating a plasma sheath around the object that glows with a characteristic spectrum determined by the mineral composition of the rock itself. Silicate minerals produce specific emission lines. Iron produces others. The combination of these signatures creates what is essentially a spectral fingerprint of the object's composition, and that fingerprint is distinct from the chemical signatures produced by any known explosive, propellant, or weapon system. Spectrographs and all-sky cameras operated by meteor-observing networks capture these signatures automatically. The data from Ohio and Houston was examined by multiple independent research groups, and the spectral signatures were consistent with natural stony meteorite composition in both cases. Beyond the optical signatures, there are the infrasound signatures. The global network of infrasound monitoring stations, low-frequency sound detectors originally deployed specifically to detect nuclear weapons tests under the Comprehensive Nuclear Test Ban Treaty, recorded both events automatically. Infrasound signatures from natural airbursts have a specific waveform character determined by the altitude, energy, and geometry of the explosion. They look different from chemical explosions. They look different from nuclear detonations. They look different from hypersonic weapons impacts. The waveform characteristics recorded for Ohio and Houston are consistent with natural bolide airbursts at the altitudes and energies reported, and inconsistent with any artificial weapons signature in the monitoring network's reference library. These systems were built specifically to tell the difference between natural and artificial atmospheric explosions. They are very good at their job. Both events read as natural. Military satellites designed to detect ballistic missile launches and nuclear detonations also observed both events, as they observed most significant fireball events globally. The optical sensors on these platforms are sensitive enough to detect the thermal pulse from a natural bolide airburst, and they have decades of reference data distinguishing natural events from artificial ones. The data from these systems, where it has been made available through official channels, is consistent with natural meteorite falls in both cases. If Ohio and Houston were weapons, they were weapons that somehow perfectly replicated the spectral, infrasound, and thermal signatures of natural space rocks at every sensor system simultaneously. The simpler explanation is that they were natural space rocks. Now, the Red Oak, Texas event deserves its own moment here, because it circulated heavily on social media during this same period and got folded into the narrative by people understandably trying to connect dots in a confusing week. Video circulated online showing unusual aerial phenomena over Red Oak, lights moving in ways that prompted immediate speculation about weapons testing, advanced propulsion systems, and various other explanations. The crucial detail that gets lost in the social media version of this story is that the Red Oak event displayed flight characteristics that are specifically inconsistent with natural meteors: apparent course changes, non-ballistic trajectories, behavior that does not match an object moving under gravity and atmospheric drag alone. Rather than representing evidence of a weapons program, this inconsistency is actually the strongest argument that the Red Oak footage captured something completely unrelated to the meteor events, most likely conventional aircraft or drone operations in an area that happens to be geographically adjacent to the airburst cluster. Multiple separate and unconnected things can happen in the same general region of the country, within a few days of each other. The fact that people noticed and reported them together doesn't make them physically connected. Correlation between social media reports is not evidence of physical causation between the events being reported. The global nature of the cluster is, in the end, the argument that most cleanly eliminates the weapons hypothesis, and it's the argument that doesn't get made loudly enough in these discussions. The March 2026 cluster included a confirmed rooftop impact in Koblenz, Germany, an infrasound detection in the South Pacific, significant fireball events over the Pacific Northwest and Louisiana, the Ohio airburst, the Houston airburst, 6 events across multiple continents and ocean basins within 20 days. No military program targeting American cities, no matter how sophisticated, no matter how well-resourced, no matter how strategically conceived, would simultaneously produce confirmed meteorite impacts on residential rooftops in Western Germany and infrasound detections in the middle of the Pacific Ocean as part of the same operation. The geographic spread of this cluster is only coherent if the source is distributed in space, following orbital mechanics around the Sun, not launched from any terrestrial facility or orbital weapons platform. The weapons hypothesis requires a global conspiracy of extraordinary complexity and geographic reach to explain events that natural orbital mechanics explains completely. So the weapons hypothesis fails. It fails on spectral evidence, it fails on infrasound evidence, it fails on satellite detection data, It fails on geographic distribution. It fails on the fundamental physics of what natural meteors look like, compared to what artificial explosions look like when observed by instruments specifically designed to distinguish between them. But here is the thing about debunking it, and this is the part that should stay with you long after the conspiracy theories have been set aside. Debunking the weapons hypothesis does not make the March 2026 cluster less strange. It makes it more strange. Because when you remove the human agent from the story, when you take away the villain and the motive and the weapons program and the geopolitical framework, you are left with the actual situation in its unmediated form. 6 significant fireball events in 20 days, from no coherent source direction, with no shower affiliation, 2 of them over major American cities, at least 1 confirmed residential impact in Germany, and a probable one in suburban Houston. Doppler radar evidence of a populated area-strewn field over neighborhoods where people were home, and no complete scientific explanation currently in hand for why this cluster happened when it did and where it did. The conspiracy theory was, in a very real sense, the comfortable version of this story. It had a villain, it had a motive, it had a human being somewhere making a decision that could theoretically be stopped. The real version is harder to sit with in the dark because the real version doesn't have any of that. It just has physics and probability, and the universe operating on its own timeline, following its own rules, reminding us with patient and complete indifference that it has never once asked our permission before it acts. The real mystery is bigger than any weapon ever built, and the sky, as it turned out, was nowhere close to finished. Part 11. A strong geomagnetic storm hit at the same time. On March 20th, 2026, the day before Houston, the day of the South Pacific infrasound detection, the day the planetary defense community was still processing what had happened over Ohio 3 days earlier, the sun decided it was not going to sit this one out. A coronal mass ejection launched from the sun's surface and aimed itself, with the indifferent precision of solar physics, directly at Earth. The timing was, depending on your tolerance for cosmic coincidence, either completely unremarkable or quietly extraordinary. Ohio had just happened. Houston was 24 hours away, and somewhere in the middle of the Pacific Ocean, infrasound monitoring stations were recording the acoustic signature of yet another significant bolide event that nobody on social media had noticed yet, because it had the courtesy to explode over open water rather than over a city. The week was already unusual by any reasonable measure, and then the sun sent something our way as well, as if to clarify that the sky above us operates on multiple frequencies simultaneously, and does not consult our schedules before acting on any of them. A coronal mass ejection, or CME, is a massive release of magnetized plasma from the sun's corona, the outer layer of the solar atmosphere that burns at temperatures far hotter than the sun's visible surface, a fact that has puzzled solar physicists for decades and still lacks a complete explanation. When magnetic field lines in the corona become tangled and stressed beyond a critical threshold, they can suddenly reconnect in a violent reconfiguration that flings billions of tons of charged particles outward into interplanetary space at speeds ranging from several hundred to several thousand kilometers per second. When one of these events is directed at Earth, it travels across approximately 93 million miles of interplanetary space and arrives typically 1 to 3 days after the initial solar eruption, depending on its velocity. During that transit time, it is invisible to the naked eye, undetectable without specialized instruments, and completely unstoppable by any technology humanity currently possesses. It is, in that sense, not entirely unlike the objects that arrived over Ohio and Houston, something coming from space toward Earth on its own timeline that we can observe but cannot intercept. When the CME arrives, it interacts with Earth's magnetosphere, the magnetic bubble generated by our planet's internal magnetic dynamo, which extends tens of thousands of miles into space on the sunward side and stretches into an elongated tail hundreds of thousands of miles long on the night side. The arriving CME compresses the magnetosphere on the sunward side, pushing its boundary closer to Earth than its normal position. On the night side, the interaction stretches and distorts the magnetic tail, loading it with energy that eventually releases in substorm events that drive charged particles down along magnetic field lines toward the polar regions. This cascading interaction drives electrical currents in the upper atmosphere, heats the ionosphere, increases drag on satellites in low Earth orbit, and produces the phenomenon that most people know simply as the Northern Lights, the aurora borealis in the northern hemisphere and aurora australis in the south. In the presence of a strong enough geomagnetic storm, those auroral displays move far equatorward from their usual polar home, becoming visible to millions of people who would never see them under normal conditions. The CME that arrived March 20th was not a minor event by any standard space weather metric. Geomagnetic activity indices measured during its arrival peak reached approximately 7 on the KP scale, a 0 to 9 index of global geomagnetic disturbance. A KP of 7 corresponds to a G3 classification, a strong geomagnetic storm, the third level on a 5-level scale that tops out at G5, which is reserved for events capable of causing widespread power grid disruption and satellite damage. The magnetic field disturbance reached approximately 38 nanoteslas at its peak phase, which is a significant compression of the normal solar wind magnetic field. Auroras were confirmed visible from the northern tier of the United States. States like Minnesota, Michigan, and Wisconsin saw displays, but reports also came in from further south than that, from latitudes that typically go entire decades without seeing a single auroral display. Parts of Europe reported similar sightings. People who had never seen the northern lights from their own backyards stepped outside on the evening of March 20th and watched green and red curtains of light move across skies that had no business displaying them. For context, a G3 storm is significant enough in practical terms to cause intermittent voltage irregularities on high-latitude power transmission systems, requiring grid operators to adjust protective relay settings. Satellite operators in low Earth orbit experience increased atmospheric drag as the heated and expanded upper atmosphere extends to higher altitudes, requiring orbital corrections to maintain proper positioning. High-frequency radio communications at high latitudes experience disruption and degradation, affecting aviation communication in polar routes. These are not catastrophic effects. A G3 storm is not a civilization-threatening event, but they are real, measurable, operational impacts on technology that modern society depends on daily. Now, here is the important scientific caveat, stated as clearly as it deserves to be stated. There is no established causal mechanism linking geomagnetic storms to enhanced meteorite activity. None. The meteorites arrive from space on orbital paths determined by gravitational mechanics that have nothing to do with Earth's magnetic field. They are not deflected toward Earth by geomagnetic disturbances. They are not attracted by solar wind interactions. They are not generated by CME activity in any model that mainstream planetary science takes seriously. The solar wind that drives geomagnetic storms and the small rocky debris that produces fireballs are completely separate physical phenomena operating through completely different mechanisms with no demonstrated causal connection. Saying that a geomagnetic storm and a meteor cluster happened during the same week is a statement about temporal correlation. It is emphatically not a statement about physical causation. Anyone who tells you the CME caused the meteor events is telling you something that the physics does not support. And yet, there is a word that keeps appearing in careful scientific writing about complex systems, a word that functions as a pause button for premature certainty, and that word is nevertheless. Nevertheless, there is something worth sitting with honestly when you look at what the last week of March 2026 looked like from the perspective of Earth as a complete system, rather than as a collection of isolated events. A 7-ton rock detonated over Ohio on March 17th. A South Pacific bolide was detected by infrasound networks on March 20th. A G3 geomagnetic storm arrived at Earth on March 20th, driving auroral displays across the northern hemisphere. Houston was struck on March 21st. Within 36 hours of the Houston event, seismographs around the planet began recording significant earthquakes in multiple ocean basin locations. The Sun and the near-Earth space environment and the solid Earth were all simultaneously registering elevated activity in the same narrow window of time. These events do not cause each other. The physics is clear on that, but they happen together, and the human experience of that coincidence is not nothing, even if its scientific interpretation requires considerable restraint. We are currently in solar cycle 25, the most recent 11-year cycle of solar activity that follows the rhythmic rise and fall of the Sun's magnetic complexity. By late 2025 and into early 2026, solar cycle 25 had reached activity levels near its predicted maximum, the peak phase when sunspot counts are highest, when CME frequency is greatest, when solar flares are most energetic and most common. Solar maximum is not a sudden event. It is a broad period lasting roughly a year or two around the cycle's peak, during which the Sun is simply more active across all measures than it is during solar minimum. The CME of March 20th was not anomalous within the context of solar maximum. It was roughly what space weather forecasters expected this phase of the cycle to produce. It was, in the language of solar physics, an ordinary strong storm during an active period. But here is the thing about multiple simultaneous unusual events that is genuinely worth sitting with before we move forward. Human beings evolved over hundreds of thousands of years in an environment where the arrival of multiple threats simultaneously was a meaningful and important pattern to recognize. The cognitive architecture that causes us to notice when several things go wrong at once, when the sky becomes active in multiple ways at the same time, when the environment seems to be doing more than its baseline activity across several different dimensions, that architecture exists because it was useful. It saved lives, repeatedly, across the long arc of human prehistory. It is not always right. It produces false positives. It can generate anxiety about coincidences that are genuinely just coincidences. But it is not simply noise in the system. It is a signal detector that sometimes, under the right conditions, is detecting something real. The sky was busy in more ways than one during the last week of March 2026. The Sun was active. The near-Earth environment was delivering objects to the upper atmosphere at above baseline rates. The ground beneath our feet, as we were about to discover, was registering its own kind of activity in ways that would add one more layer to a week that was already asking more questions than the data could answer. Whether any of it connects is the question science has not yet resolved. But the next layer of the story was already underway before anyone had finished processing the one before it. Part 12. Earthquake burst. Within 36 hours. Coincidence or pattern recognition. Within 36 hours of the Houston airburst, seismographs around the planet lit up. Not metaphorically. Not in the way that science journalists sometimes reach for dramatic language to describe routine measurements. The instruments that monitor ground motion across the global seismic network, sensors buried in boreholes and vaults on every continent and ocean island, sensitive enough to detect the footsteps of a passing truck from miles away, precise enough to locate an earthquake's epicenter to within a few kilometers from the other side of the planet. Those instruments began registering significant events in a compressed window of time that, when you lay it out on a timeline next to everything else that was happening that week, produces a particular quality of stillness in the reader that is worth paying attention to. A magnitude 6.7 earthquake struck the mid-Atlantic ridge. A magnitude 6.6 occurred in Antarctica. A magnitude 6.1 hit Vanuatu in the South Pacific. Over the course of the same week, the global seismic network recorded more than 100 earthquakes of magnitude 4.5 or greater across multiple tectonic regions. To put that number in perspective without either dramatizing or dismissing it, magnitude 4.5 is the threshold at which earthquakes begin to be widely felt by people near the epicenter. 100 such events in a single week, distributed across the planet, is a number that registers above the background noise even to seismologists who spend their careers staring at data streams that are never fully quiet. For those keeping score at home, that is a significant amount of seismic activity compressed into a very short window of time, and it arrived in the same week as two major airbursts over American cities, a G3 geomagnetic storm, a South Pacific bolide detection, and a close asteroid approach that we actually managed to see coming for once. The week of March 17th through March 23rd, 2026 was, by any reasonable accounting, an unusual week to be a planet. Before we go any further, let's be honest about what this means and what it doesn't mean, because the internet is extremely good at connecting unconnected dots, and extremely bad at stopping to ask whether those dots are actually adjacent to each other in any physically meaningful sense. Earthquake science has a well-characterized global baseline developed over more than a century of continuous instrumental monitoring. The planet experiences somewhere between 12 and 20 significant earthquakes, magnitude 6 or greater, per year on average, with considerable variation from year to year driven by the inherently stochastic nature of fault rupture processes. The distribution of seismic activity across the globe is highly non-uniform. It concentrates along tectonic plate boundaries, where crustal plates are colliding, separating or sliding past each other, and the friction and stress accumulation along those boundaries periodically releases in earthquakes that range from imperceptible microseisms to civilization-altering megathrust events. The Mid-Atlantic Ridge is one of the most seismically active linear features on Earth, a divergent boundary running roughly north to south through the center of the Atlantic Ocean, where the North American and Eurasian plates are separating at a rate of a few centimeters per year. Earthquakes along the ridge happen constantly, continuously, and almost entirely in open ocean, where they affect nothing and no one. A magnitude 6.7 event along the ridge is scientifically unremarkable. It is the ridge doing what the ridge does, at a size it does regularly, in a location that generates no humanitarian concern and no infrastructure damage. Antarctica's seismic event occurred in a region of complex tectonic interaction at the margins of the Antarctic plate, in a location where essentially no permanent human population exists to experience any surface effects. Vanuatu sits directly on the Pacific Ring of Fire, in one of the highest seismic hazard zones on the planet, where magnitude 6 earthquakes occur with a regularity that makes each individual event a routine entry in the monitoring catalogue rather than a headline. Individually, each of these events has a completely mundane tectonic explanation, requiring no exotic causal mechanism, no unusual triggering process, and no connection to anything that was happening in the atmosphere or in near-Earth space during the same week. Plate boundaries accumulate stress over years and decades and centuries, and they release that stress when the accumulated strain exceeds the frictional strength of the fault surface. That process operates on geological timescales that are utterly indifferent to what is happening in the sky above. The rocks do not know about the meteors, the faults do not respond to solar storms. The seismic catalogue for the week of March 2026 is elevated relative to the short-term average, but it is not outside the range of normal variation when viewed against the full historical record. That is the scientific baseline position, and it is the correct starting point for any honest analysis of this data. Where things get philosophically interesting, not scientifically established, let that distinction be absolutely clear, but philosophically interesting in a way that deserves engagement rather than dismissal, is in the question of whether geomagnetic storms can influence the timing of earthquakes on faults that are already near their failure threshold. This is a genuinely controversial area of research, sitting at the uncomfortable boundary between mainstream geophysics and hypotheses that the mainstream community views with significant skepticism. A small but persistent scientific literature, produced by researchers at credible institutions using real data and real statistical methods, has explored correlations between geomagnetic disturbances and subsequent seismic activity in various regions and time windows. The proposed physical mechanism involves the induction of electrical currents in electrically conducting rock by rapidly varying geomagnetic fields, the same electromagnetic induction process that drives current in a wire moving through a magnetic field applied to the conductive minerals in crustal rock near active fault zones. In theory, these induced currents could generate localized heating or pressure changes that might nudge a fault already critically stressed toward the rupture threshold, slightly earlier than it would have ruptured on its own. The mainstream geophysics community treats this hypothesis with skepticism for two distinct reasons that are worth separating. The first is mechanism plausibility. The magnitude of induced currents expected from even a strong geomagnetic storm is extremely small, compared to the stress levels operating on major fault systems, making it physically difficult to construct a convincing model in which the electromagnetic perturbation is large enough to matter. The second is statistical robustness. The studies claiming to find correlations have generally struggled to survive rigorous replication attempts and have been criticized for methodological choices that may inflate the apparent strength of the association. These are legitimate scientific objections. The hypothesis is not accepted by the field, and that non-acceptance is based on substantive technical grounds rather than mere conservatism. But the honest answer to the question of whether the G3 geomagnetic storm of March 20th influenced any of the seismic events that followed in the subsequent 36 hours is this: we do not know with certainty. We do not have a confirmed mechanism. We do not have statistical proof that rises to the standard the geophysics community requires for causal claims. What we have is temporal correlation in a week that contained more than its share of things happening at once, in a solar cycle that was near its maximum, in a near-Earth environment that was delivering space rocks to populated areas at above baseline rates. Correlation without causation is a real and common phenomenon. It is also true that all causal relationships, before they are understood, begin as correlations that someone decided were worth investigating rather than dismissing. What the human brain does with simultaneous unconnected events, meteors, solar storms, earthquakes, close asteroid approaches, is seek narrative unity. We are, at the most fundamental neurological level, story-making machines. We look at a collection of data points distributed in time and space, and we reach, almost involuntarily, for the thread that connects them into a coherent sequence with a beginning, a middle, and an implication about what comes next. Related events are comprehensible. They can be modeled, predicted, responded to. Random, simultaneous events are deeply unsettling precisely because they resist that narrative structure. They just happen, all at once, for no unified reason, and then they stop, and the next cluster of simultaneous events will have nothing to do with this one except the accident of temporal proximity. The rational response is to hold the correlation honestly while resisting the very powerful temptation to convert it into causation without the evidence that causation requires. Everything that happened in the last week of March 2026 has individual explanations that are complete and sufficient without any exotic connections between them. An unusual meteor cluster driven by an as-yet uncharacterized change in the near-Earth debris environment. A solar maximum CME event of the kind that solar cycle 25 was always going to produce. Tectonic stress release along boundaries that were always going to rupture on their own schedule. Whether those individual explanations are the entire and complete picture, or whether they are each accurate as far as they go while missing something larger that connects them, that is a question that the current data cannot resolve, and that intellectual honesty requires us to leave open. Everything that happened had an explanation. Whether the explanation was the whole story is something else entirely. And while all of this was unfolding, the airburst cluster still being processed, the storm data still being analysed, the seismographs still recording aftershocks from events that had no connection to anything falling from the sky, another object was already on its way past Earth. This one, for once, we actually saw coming. And what that tells us about what we can and cannot see is, in some ways, the most important part of this entire story. Part 13, Asteroid 2026. FU, a close pass we did see. On approximately March 22nd, 2026, while the scientific community was still processing the Houston airburst, while fragment hunters were beginning to organize searches across the northern suburbs, while a woman in Spring, Texas was waiting to find out whether the rock on her floor was going to make history, an asteroid designated 2026 FU slipped past Earth at a distance of roughly 0.004 astronomical units, approximately 1.5 times the distance from Earth to the Moon. Close enough in the language of planetary defense to matter, far enough in the language of actual risk to pass without incident. It came and went without shaking a single wall, or triggering a single car alarm, or depositing a single fragment in a single suburb anywhere on the planet. And the reason that quiet, uneventful close approach is one of the most important parts of this entire story is not what 2026 FU did. It is what it tells us about the difference between the objects we can see and the objects we cannot. To translate 0.004 astronomical units into human terms requires a brief detour through scale, because astronomical units are the kind of measurement that sounds precise without feeling real. 1 astronomical unit is the average distance from Earth to the Sun, approximately 93 million miles. 0.004 of that is roughly 372,000 miles. The Moon orbits Earth at an average distance of about 239,000 miles. So 2026 FU passed at approximately 1.5 times the Earth-Moon distance, well inside the orbital radius of the Moon, in the region of space where our own natural satellite traces its monthly path. In astronomical terms, 0.004 astronomical units is the difference between a comfortable conversation across a table and someone standing close enough that you can smell their coffee. It is not a near miss in the dramatic sense that science fiction uses that phrase, but it is unambiguously close in any framework that takes planetary defense seriously. 2026 FU was traveling at approximately 4.4 kilometers per second relative to Earth at closest approach. That velocity is slower than the objects that produced the Ohio and Houston airbursts, significantly slower in fact. Ohio's object was moving at roughly 45,000 miles per hour, which converts to approximately 20 kilometers per second. Houston's object was moving at approximately 35,000 miles per hour, or about 15.6 kilometers per second. 2026 FU, at 4.4 kilometers per second, was moving at roughly one-fifth the velocity of the objects that actually hit us. This matters for impact energy calculations. Kinetic energy scales with the square of velocity, so a slower object of equivalent mass delivers dramatically less energy on impact. But it also matters for detection, because slower objects spend more time in detectable positions and are easier for survey telescopes to find and track against the background of fixed stars. The crucial fact about 2026 FU is contained in a single word. It was detected before its closest approach, not after, not during, before. Exactly how far in advance the detection occurred is not precisely specified in publicly available data at the time of this reporting, but the sequence is confirmed. Survey telescopes found it, calculated its trajectory, determined it would pass close but not hit, and tracked it through its closest approach without incident. This is the planetary defense system doing exactly what it was designed to do, executing its intended function within its operational parameters, producing the outcome that justifies the investment in survey infrastructure. Something came within 1.5 lunar distances of Earth, and we knew it was coming before it arrived. Hold that sentence next to what happened 4 days earlier over Ohio and 5 days earlier over Houston, and let the contrast do its work without any editorial assistance. We knew 2026 FU was coming. We knew nothing about either object that actually hit us until the light reached someone's eyes, and the sound reached someone's ears, and the shock wave reached someone's walls. The detection system found the object that passed safely and missed entirely the objects that exploded over cities. This is not a failure of intent. It is not a failure of effort. It is a structural consequence of the physics of detection applied to objects of different sizes approaching from different geometries, an understanding that structure is essential to understanding what planetary defense can and cannot currently promise us. The reason 2026 FU was detectable, and Ohio and Houston were not, comes down to two factors that interact in ways that define the entire capability envelope of current survey systems. The first factor is size. 2026 FU is substantially larger than either of the objects that produced the American airbursts. Larger objects have greater surface area, reflect more sunlight, and are therefore brighter against the background sky when viewed from Earth-based telescopes. Brightness is the primary currency of asteroid detection. Survey systems find objects by detecting their reflected light, and an object that reflects too little light to exceed the sensitivity threshold of available instruments is effectively invisible to those instruments regardless of how close it gets. Ohio's 7-ton object and Houston's 1-ton object were simply too small and too dark to appear in any survey telescope's field of view at a distance that would have allowed meaningful advance warning. 2026 FU was large enough to be bright enough to be found. The airburst objects were not. The second factor is approach geometry. The direction from which an object approaches Earth determines whether it spends time in regions of sky that survey telescopes can efficiently monitor. Objects approaching from the direction of the Sun are hidden in solar glare and are essentially undetectable by ground-based systems until they emerge from the Sun's vicinity, at which point they may already be extremely close to Earth. Objects approaching from favourable geometries, arriving from parts of sky that survey telescopes cover regularly, and at angles that give them time in the detectable zone, are far more likely to be found. 2026 FU apparently approached from a geometry that made it accessible to current survey networks. Ohio and Houston apparently did not. This is not a conspiracy. It is orbital mechanics. The selective nature of this detection creates what philosophers of science call an epistemic problem, a problem not just with what we know, but with our ability to know what we don't know. Our catalogue of near-Earth objects is genuinely excellent for large bodies. Objects over 1 kilometre in diameter that could cause civilization-scale damage on impact are estimated to be over 95% catalogued. We have found almost all of them. We know their orbits. We can project their trajectories centuries into the future and confirm that none of them are going to hit us in any time frame that current civilization needs to worry about. That is a genuine and remarkable scientific achievement built over decades of systematic survey work. But the catalogue thins with extraordinary rapidity as object size decreases. Objects over 140 metres in diameter, large enough to devastate a major metropolitan area or a small country, are estimated to be perhaps 40% catalogued. More than half of them are unknown, their orbits uncharacterized, their future trajectories uncalculated. Objects in the 10 to 50 meter range, the size class that includes the Chelyabinsk impactor and objects substantially larger than Ohio and Houston, are catalogued at a tiny fraction of their estimated total population. And at the meter to 10 meter scale where Ohio and Houston lived, the catalogue is not incomplete. It is essentially non-existent. We have no systematic inventory of objects in that size range. We cannot tell you how many there are. We cannot tell you where they are. We cannot tell you whether the March 2026 cluster represents a statistically normal fluctuation in a population we simply haven't been measuring carefully, or whether something has changed in the near-Earth environment that elevated the flux of small objects during that specific window. We cannot distinguish between those two scenarios because we lack the observational data that would allow the comparison. You cannot measure a deviation from a baseline you have never established. And for meter-scale objects, we have no baseline. We have events, Ohio, Houston, Chelyabinsk, the thousands of smaller events that occur globally each year, but we do not have a complete population model from which to calculate expected rates and compare them to observed ones. The gap in our knowledge is not a gap we can currently see across. It is a gap whose far side we cannot locate. We are not fully blind. 2026 FU proves that. The system works, for the objects it was built to find, at the sizes and geometries it was optimized for. But we are not fully seeing. Ohio and Houston prove that equally clearly. And the space between those two conditions, between the objects we can find and the objects the solar system actually contains, in the size ranges that can shake cities without warning, is not a narrow gap that will close naturally with modest improvements to existing systems. It is a structural feature of our current detection architecture that requires deliberate, substantial, and urgent investment to address. The frustrating truth about planetary defense in 2026 is not that we're doing nothing. What we're doing is genuinely impressive, seriously funded and staffed by researchers of the highest caliber, working with real dedication on a problem that genuinely matters. It is that what we are doing is simultaneously impressive and insufficient, and those two things are both true at the same time without contradiction. Impressive for large objects that could end civilization, insufficient for the ones that are small enough to arrive completely unannounced, and large enough to detonate over the fourth largest city in America and rattle the walls of every house within 150 miles. The upgrade that would close that gap is coming. The observatory that could change what we see, how fast we see it, and how far ahead of arrival we can calculate a trajectory, that instrument is nearly ready. It is sitting on a mountain in Chile, fully built, waiting to begin its survey of a sky that has been delivering surprises all month. It is almost ready. The sky, unfortunately, is not waiting for almost. Part 14, Artemis. 2. Humanity moves forward. Anyway. On March 19th, 2026, 2 days after the Ohio airburst had rattled windows across multiple states, 2 days before Houston would shake the walls of 7 million people's homes, in the precise middle of the most unusual week in recent memory, for anyone paying attention to what was falling from the sky, NASA rolled the Space Launch System rocket for the Artemis II mission out to Launch Complex 39B at Kennedy Space Center in Florida. The crawler transporter that carries the SLS stack from the Vehicle Assembly Building to the launch pad moves at a maximum speed of approximately 1 mile per hour. It is the slowest possible way to begin a journey that will eventually take human beings 250,000 miles from Earth. The contrast between that deliberate, grinding mechanical patience and the 35,000 miles per hour at which Houston's object would arrive 48 hours later is the kind of detail that doesn't make it into official press releases, but lodges itself permanently in the mind of anyone who notices it. The rocket that humanity is sending towards space moves at 1 mile per hour on its way to the pad. The space that humanity is reaching toward sends things back at 35,000. The relationship between our species and the cosmos has always had this quality of asymmetry, and the week of March 17th through March 23rd, 2026 made that asymmetry unusually visible. The Artemis II mission is the first crewed lunar flyby in over 50 years. Not a landing, Artemis II is a free return trajectory, a figure-8 path that carries the crew out to lunar distance, swings around the moon using its gravity, and returns them to Earth without a powered descent to the surface. That profile was chosen deliberately for the second Artemis mission, as a way of certifying the Orion spacecraft and its life support systems, with crew aboard before committing to the more complex powered descent required for landing. But even without a landing, Artemis 2 carries human beings further from Earth than any person has travelled since Eugene Cernan climbed back into the lunar module at Taurus Littrow in December of 1972, and became, without anyone fully appreciating it at the time, the last human being to stand on another world. More than 50 years have passed since that moment. 2 generations of scientists, engineers and astronauts have lived their entire professional careers in a period when humanity's reach stopped at low Earth orbit. Artemis 2 is the mission that ends that period. The Space Launch System is currently the most powerful launch vehicle ever successfully flown, producing approximately 8.8 million pounds of thrust at liftoff from its core stage engines and solid rocket boosters combined. It is a machine of extraordinary engineering complexity built over more than a decade at a cost that generated considerable congressional debate, and its rollout to the launch pad on March 19th was a moment of institutional significance for NASA and for the broader human spaceflight program, regardless of whatever else was happening in the sky that week. The crawler transporter made its slow way along the crawlerway, while, somewhere above the same state of Florida, the atmosphere was quiet. Ohio had already happened. Houston had not yet happened. For those 48 hours between the 2 events, the rollout proceeded in a window of relative calm that would not last. There is something genuinely remarkable about the juxtaposition of those 2 facts existing within the same week, in the same country, under the same sky. A nation whose atmosphere had just been shaken by a 7-ton rock arriving without warning, and which would be shaken again in 2 days by a 1-ton rock arriving with equal silence, was simultaneously preparing to send 4 human beings further into the environment those rocks came from than anyone had ventured in half a century. Whether that strikes you as inspiring or deeply ironic probably reveals something about your general relationship with the concept of existential risk. But both readings are entirely valid, and neither cancels the other out. The inspiring reading goes something like this: the fact that space occasionally sends things our way, that the near-Earth environment contains objects that can and do enter our atmosphere without warning, that the boundary between outer space and the inside of someone's house is thinner than most people spend any time contemplating. None of that changes the fundamental calculus of why human beings should go to space. If anything, it strengthens it. The best defense against an environment you don't fully understand is to go into that environment and study it directly, to build infrastructure that lets you observe it continuously, to develop the capability to operate within it rather than simply endure what it delivers to you passively. Artemis is not a vacation program. It is the beginning of a permanent human presence in the cislunar environment, the region of space between Earth and the Moon, that over decades and generations will give humanity the capability and the knowledge to understand and eventually respond to the threats that environment contains. The Moon itself is directly relevant to this story in ways that go beyond the symbolic. The lunar surface is the solar system's most accessible long-term record of impact history. Unlike Earth, which erases its impact craters through weathering, erosion, plate tectonics, and biological activity, the Moon preserves its craters essentially forever. Every impact event that occurred in the inner solar system over the past 4 billion years left a mark on the lunar surface that is still there, still measurable, still available for study. The size distribution of craters tells you the size distribution of impactors. The age distribution of craters, determined by radiometric dating of returned samples, tells you how the impact rate has varied over time, when the inner solar system was more crowded with debris, when it was less, what the baseline looks like across geological timescales that make the 20-day window of March 2026 look like a single frame in a 4 billion-year film. Artemis astronauts returning to the lunar surface with modern analytical instruments and the full toolkit of 21st century field geology will be able to read that impact record at a resolution and completeness that Apollo-era sampling only hinted at. They will be able to answer questions about the early solar system's bombardment history that are directly relevant to understanding the current near-Earth environment, including whether periods of elevated impact flux have occurred before, what caused them, how long they lasted, and what they looked like from the ground. The Moon is, among many other things, the best planetary defense research station in the solar system, and it has been waiting for us to come back and read it properly for 50 years. The Artemis 2 crew, Reed Wiseman, Victor Glover, Christina Koch, and Canadian astronaut Jeremy Hansen will not land on the Moon on this mission, but they will travel to lunar distance. They will look back at Earth from a vantage point that no human being has occupied since 1972. And from that distance, the planet they are looking at will appear as it actually is in the cosmic context. A small blue sphere moving through a solar system that contains an enormous amount of debris at every size scale, from microscopic dust to civilization-threatening rocks, most of it invisible to the instruments currently watching for it, all of it following orbital paths that intersect Earth's own path with a frequency that the week of March 17th through March 23rd made suddenly and uncomfortably personal. There is a deeper resonance in that image than any press release will articulate. The Artemis II crew will be physically present in the environment from which Ohio and Houston's objects came. They will be floating in the same interplanetary space through which those rocks travelled before they hit our atmosphere. The abstract discussion of near-Earth objects, of detection gaps and strewn fields and radar-confirmed fragment, falls over suburban neighbourhoods, becomes something different when you're inside the environment, rather than looking up at it from the ground. The astronauts will not be in danger from the kind of small objects that produced the American airbursts. The probability of their spacecraft encountering a significant object during their brief lunar trajectory is vanishingly small. But they will have a relationship with that space, an embodied understanding of it that no amount of telescope observation or data analysis from the ground fully replicates. We are, as a species, doing two things simultaneously right now that feel contradictory, but are actually the same thing viewed from different angles. We are being reminded through Ohio and Houston, and the radar-confirmed strewn field over Willowbrook and Northgate Crossing, that space comes to us whether we are ready for it or not, on its own schedule, without warning, without asking whether we have finished building our detection systems yet, and we are choosing, through Artemis II and the broader architecture of human space exploration that it represents, to go toward that same space anyway, deliberately, carefully, 1 mile per hour at a time on a crawler transporter, and then very much faster once the engines light. This is not recklessness. It has never been recklessness. It is the most characteristically human response available to a species that has always lived in an environment that could kill it. To study that environment directly, to build knowledge about it systematically, to develop capability within it incrementally, and to refuse, generation after generation, to let the possibility of being hit make us stop moving toward the thing that is hitting us. The rockets are rolling. The crew is ready. The sky is busy in ways we are only beginning to understand. And somewhere out there, in the orbital environment through which Artemis II will briefly travel, more objects are in motion on trajectories that intersect our future in ways we cannot yet calculate. We are reaching outward with everything we have, and the instruments that might finally let us see clearly in both directions at once are closer to ready than they have ever been. Almost, but not quite yet. Part 15. The Vera Rubin Observatory. The clock is ticking. There is a telescope in Chile that is about to change what we can see, and the most important word in that sentence is about. Not has changed, not is changing, about to. The instrument that could redefine humanity's relationship with the near-Earth object population, that could push our detection threshold to smaller sizes and greater distances than anything currently operating, that could give us hours or days of warning for events that currently arrive with zero notice. That instrument exists, it works, it is sitting on a mountain in the Chilean Andes fully assembled and increasingly operational, and it is not yet doing the job it was built to do at the cadence and completeness that job requires. The gap between almost ready and actually ready is, in normal circumstances, an administrative detail. In the context of March 2026, it is the entire story. The Vera Rubin Observatory sits on Cerro Pachón, at an altitude of approximately 8,800 feet, in the Atacama region of Chile, in one of the driest and most optically stable atmospheric environments on Earth. The site was chosen after years of systematic evaluation of candidate locations around the world, because building the most capable sky survey telescope ever constructed, and then putting it somewhere with mediocre seeing conditions would be like installing the world's most sensitive microphone in a room next to a highway. The atmosphere above Cerro Pachón is steady, dry, and dark in ways that most of the planet's surface is not, and those qualities are not luxuries for a survey telescope of Rubin's design. They are requirements. The primary instrument is the Legacy Survey of Space and Time camera, the LSST, which holds the distinction of being the largest digital camera ever constructed for astronomical purposes by a significant margin. 3.2 billion pixels. To put that number in a context that means something, a typical modern smartphone camera captures somewhere between 12 and 50 megapixels. The LSST contains 3,200 megapixels arranged across a focal plane approximately 2 feet in diameter, roughly the size of a small dining table. When the telescope points at the sky and opens its shutter, it captures an image covering an area equivalent to approximately 40 times the full moon in a single exposure. 40 full moons, in one image, in one moment, at a sensitivity that can detect objects billions of times too faint for the naked eye. And then it moves to the next field, and the next, and the next. Night after night, survey after survey, building a time-lapse record of the entire available sky that repeats every few nights with enough consistency to detect anything that has moved, brightened, faded, or appeared where nothing was catalogued before. The technical term for what Rubin is designed to detect is transients, astronomical objects or phenomena whose brightness or position changes on human observable timescales. Asteroids are transients. They move against the background of fixed stars between one image and the next. They appear as streaks or as point sources that shift position between revisits. Rubin's combination of wide field, deep sensitivity, and high cadence was engineered specifically to find them in unprecedented numbers at unprecedented distances with unprecedented speed. For planetary defense, the numbers are extraordinary. Estimates from the planetary science community suggest that within the first few years of full survey operations, Rubin will detect more near-Earth objects than all previous surveys in the history of astronomy combined. Not more per year, more total. The cumulative catalogue of near-Earth objects built by every telescope, every survey program, every automated detection system ever operated before Rubin will be surpassed by Rubin alone within a few years of it reaching operational cadence. It will push the detection threshold, the minimum size of object that can be systematically found and catalogued, to smaller diameters and at greater distances from Earth than anything currently operating can achieve. Objects that currently arrive as complete surprises, the way Ohio and Houston arrived, will begin appearing in the catalogue days, weeks, or months before their closest approach, their trajectories calculated, their impact probabilities assessed, their arrival times predicted. Not all of them. The physics of reflected light and orbital geometry means there will always be objects that approach from unfavourable directions, that arrive too fast for even Rubin's survey cadence to catch in time, that are simply too small to generate a detectable signal at any distance that allows meaningful warning. The meter-scale objects, the 1-ton rocks like Houston's impactor, will likely remain below Rubin's systematic detection threshold even at its full operational capability. The detection gap will narrow dramatically. It will not close completely. But the objects in the 10 to 100 meter range, the Chelyabinsk scale impactors and larger, will become findable in a way they currently are not, and that improvement represents a qualitative change in the risk landscape for the size class of objects that can cause regional devastation. The observatory has been under construction and commissioning for years, the product of a collaboration involving the Department of Energy, the National Science Foundation, and an international consortium of research institutions that recognized collectively that the next generation of sky survey capability required an instrument of this scale and sophistication. Full science operations, the steady-state survey cadence that will produce the detection rates and catalogue completeness that the planetary defense community has been anticipating, is imminent as of the events of March 2026. The system exists, the camera works, the software pipeline that automatically detects moving objects in the image stream, flags potential near-Earth objects, and alerts follow-up observers has been developed and tested. The infrastructure connecting the mountaintop observatory to the data processing facilities that will handle the enormous nightly data volume is in place. What separates the current moment from the era of full Rubin operations is not missing hardware or unresolved engineering problems. It is the patient, painstaking, non-negotiable process of commissioning, of calibrating the instrument across its full operational range, validating the detection pipeline against known objects, establishing the baseline measurements that allow the system to know what changed between one night's images and the next. Commissioning cannot be rushed without compromising the data quality that makes the survey scientifically useful. Every shortcut taken during commissioning is a source of systematic error that propagates through the entire catalogue, potentially causing real objects to be missed or non-existent objects to be flagged. The people doing this work are doing it correctly and as quickly as correctly allows. The timeline is what it is because the science requires it to be. And the objects are not waiting for it. This is the fundamental temporal tension of planetary defense in 2026, stated as plainly as it deserves to be stated. We are in the transition window between the surveillance capability we currently have and the surveillance capability we are actively building. Ohio arrived in that window. Houston arrived in that window. The entire March 2026 cluster, 6 significant events in 20 days, 2 of them over major American cities, one of them depositing a radar-confirmed strewn field over populated suburban neighborhoods, one of them potentially punching through a residential roof, happened in that window. The next event will happen when it happens, on orbital mechanics that don't consult human construction schedules, and whether it happens before or after Rubin reaches full operational cadence is a question that probability cannot currently answer. Here is the thing about that uncertainty that is worth sitting with as we assemble everything we know about March 2026 into a coherent picture. The Vera Rubin Observatory would not have saved Ohio or Houston, even if it had been fully operational on March 1st. The meter-scale objects that produced those airbursts are likely below Rubin's detection threshold at the distances and approach geometries involved. What Rubin would have done, what Rubin will do, once operational, is characterize the population of objects in Earth's current orbital neighborhood well enough that we can begin to ask the questions that March 2026 raised and currently cannot answer. Is the near-Earth small object population elevated right now compared to historical baselines? Is the 3-eye atlas debris hypothesis testable through population statistics rather than just through recovered sample chemistry? Are there more clusters like March 2026 in the near future, and can we see them assembling in the data before they start arriving? These are the questions that Rubin was built to answer, and it is almost ready to start asking them. The events of March 2026 happened the way all impacts have always happened throughout the 4.5 billion year history of this planet, without asking permission, without announcing themselves through any channel that the inhabitants of the target location could hear in advance, without waiting for the detection infrastructure to be ready. Ohio and Houston joined the long, unrecorded list of impacts that preceded them across deep time, most of them witnessed by nothing capable of reporting what it saw, all of them equally indifferent to the preparedness of whatever was living beneath the point of arrival. The question that remains, after all the data is assembled and all the fragments analyzed and all the isotope ratios returned from the laboratory, is the question that honest science must leave open when the evidence does not yet resolve it. Is March 2026 an anomaly, a statistical cluster that future researchers will explain as ordinary variance in a Poisson process, unremarkable in retrospect, just the random distribution doing what random distributions occasionally do? Or is it the beginning of a pattern that was always there, always arriving, always real, but only became visible to us when it started happening over cities instead of oceans? We don't know. The data is incomplete. The analysis is ongoing. The observatory is almost ready. And the next event is already somewhere in the solar system, moving toward its intersection with Earth's orbit on a timeline that belongs entirely to physics and not at all to us. We have always believed that space was something we reached toward on our own terms, when we decided we were ready, at a pace we controlled. March 2026 spent 4 days reminding us, with the patient and complete indifference of the universe, that space has never agreed to those terms, was never waiting for our readiness, and has been arriving on its own schedule since long before there was anyone here to notice. It is not finished yet, and neither are we.